Hello, virtual March meeting. I'd like to take a minute to tell you about a very simple loss-tolerant extension of the Barrett-Koch protocol for entanglement generation. And at the very end, spend a little bit of time talking about general methods for designing quantum feedback protocols. So, first of all, what is Barrett-Koch? Well, it's in the context of using measurement for entanglement generation. And that'll be the broad topic of what I'll talk about today. So among the many applications of measurement, one of the somewhat more subtle applications is the generation of entanglement for weakly or non-interacting quantum systems. So for example, in the setup that I've shown here, this is a common setup for creating heralded entanglement between remote spins. This is actually the method that was used to implement the first loophole-free violation of the Bell's inequality, for example. So that's a good way to make Bell pairs. And another common example is for spin squeezing, where in cold neutral atoms, people have used measurement as a resource to create spin squeezing, which is a useful metrological tool for quantum sensing and quantum clocks. So a downside of using measurement for control, although it's useful for creating entanglement, is that measurement is an inherently random process in quantum mechanics. And so you're inevitably going to generate some amount of randomness into any protocol that relies on measurement too much. So the main sort of overarching goal of this talk is to talk about how to use quantum feedback to gain more control of the measurement process and remove some of this inherent randomness. So an important caveat in the beginning is that because I'm talking about doing feedback during a measurement, so actually for an atomic quantum system, this would actually be doing feedback during the spontaneous emission lifetime. This is going to be completely irrelevant for a lot of quantum networking applications where you're talking about interfacing qubits that are kilometers away. Though there are a couple important exceptions to this that I'll mention toward the end. But I'm more imagining a modular quantum platform where you have either a bunch of qubits on a chip that need to be interfaced rapidly but are too far away to interact directly, or a couple of modules of qubits that are separated, maybe on the order of millimeters to meters. And these are both situations where heavy optimization of the rate of entanglement generation is going to be crucial, because entanglement generation will form a bottleneck for a lot of modular quantum computing infrastructure. So first of all, we're talking about a generalization of Barrett-Koch, so I should review what the original Barrett-Koch scheme looks like. So you might have also heard this called time bin entanglement generation, or time bin based entanglement swapping. And essentially, it's a way of creating remote Bell pairs in a way that's robust to loss in the link that connects your quantum system. So this has been a ubiquitous protocol. It's been used in trapped ions, neutral atoms, superconducting circuits, and V-centered quantum dots. And I'll quickly describe the high-level intuition of how it works. So the protocol tells you to initially take your two atoms that you want to entangle and prepare them in a superposition of this up state and this E state. And the premise is that this E state is optically active, and so it spontaneously emits and then decays to a metastable state labeled as down. And so if we have these two atoms set up so that the spontaneous emission has equal frequency and decay rate, then these photons are indistinguishable. And so what that means is if you let those photons interfere onto a beam splitter, then you get Hong-Mantel interference, and it's impossible to tell if you detect a photon from which atom that photon came. Why is that useful? Well, imagine you now have put photon counters at the other end of these beam splitters, and you measure. So if you get 0 clicks, that means you projected your system into a state in which it was never in EE, and so you project into the up state, because that's a case where there was no excitation that could decay from E to down. And if you get 2 clicks, well, that means that you got an excitation from both atoms, and so you must have collapsed down to the down state, and so you wind up in down, down. And so neither of these states have entanglement. But if you get exactly 1 click, you don't know from which atom the photon came that generated that click. And so you're in a superposition of down, up, and up, down. And because of indistinguishability, it's impossible to tell which atom is in up and which is in down. And so you wind up in a superposition of both, which is an entangled state. So you notice that this protocol is going to give you entanglement 50% of the time. And it turns out that this is actually a fairly fundamental property of experimental systems like this. So if you use the resources that I've depicted in this figure here, there's a no-go theorem that says you can't do an entangling protocol that's going to have a higher success probability than 50%. And this is coming from the fact that you actually can't implement a unit fidelity Bell measurement using sort of the resources of like vacuum ancilla and beam splitters and linear optics. So how do we get around this? The fundamental advantage I'm going to show you here is essentially a deterministic version of the protocol that I showed you on the previous slide. And it's going to let you, even in the presence of loss, double the success rate of the standard Barrett-Koch protocol. So the way this protocol works is instead we're going to initialize our atoms in EE instead of E down, or E up plus up E, and let them emit onto our beam splitter just like before. And after some time interval, you're going to detect a click on one of these photon counters, and that actually immediately prepares the entangled state E down plus or minus down E. And the sign depends on which photon counter registered the click. So we're normally used to thinking about photon bunching, so that means that if one photon goes to one beam splitter, then the other photon has to go to the same one. But an important fact to keep in mind is that there is still a fundamental timescale associated with those click events, and that timescale is the spontaneous emission rate of the atoms. And so there's always going to be some finite time interval between the first and second click. And so all you have to do, it turns out, is to apply a pi pulse on the up-down transition of this atom. That's why this is such a simple feedback protocol. And now, if you detect another click, that immediately projects you uniquely into the down-up plus or minus up-down state, which is an entangled state. And as long as you detect two clicks, it doesn't matter how much loss was experienced in the transmission line leading to these detectors. You know you detected two clicks. The environment can't have detected any because there were only ever two excitations in the system to begin with, and therefore you wind up in a unit fidelity Bell state. And this protocol is robust to sort of all the standard things that make the Barrett-Koch protocol useful for its own robustness. It's robust to loss in this channel, inefficiency of the photon counters. It's also robust to path length fluctuations or imbalance in the reflection coefficient of this beam splitter. It's even robust to the feedback delay incurred in this protocol, because if you don't do this pi pulse in time, you can actually just herald that and throw those instances out. So it decreases the success rate without decreasing the entanglement fidelity. And finally, it's robust to like non-Markovian effects that you would get from putting these atoms in Purcell-enhancing cavities, which is a common thing you have to do for these kinds of experiments. So we've taken Barrett-Koch, we've added feedback, and we've doubled the success rate with the same robustness. Now, for a lot of atomic systems, this would be quite difficult to do. For example, for NV centers where your spontaneous emission lifetime is on the order of nanoseconds, it's going to be difficult to do this kind of feedback. But there's at least one example of an atomic system where this could be very practical, and that's the erbium-doped yttrium orthosilicate, which has the benefit of is it has spontaneous emission of a telecom band, so very low loss. You can send these photons over long length scales. But it also has a very slow spontaneous emission lifetime. So you could imagine doing this kind of protocol over kilometers, given the 1 millisecond optically excited state in this defect. And also in superconducting circuits, where you can tune the spontaneous emission lifetime of qubits with like bath engineering techniques. So in the previous couple slides, I gave you one example of where thinking about doing measurement or doing feedback during the measurement process gives you some new capabilities and lets you create better entanglement. And so in the next couple minutes of my slides, I'll talk about sort of more generally how to use that concept and how you might actually derive feedback protocols for creating entanglement. I'm going to be imagining a system where you have a quantum state, and ultimately your goal is going to be to, maximize the expectation value of some operator, or maybe take your system and put it in a target state. So those are the kind of some general figure of merits that you might imagine. And when we're thinking about measurement continuously, for the experts in the audience, you would normally describe it with a master equation like this. This is called the diffusive measurement, so it's different than the photon counters seen in the previous slide, but it's more analogous to doing like homodyne detection or measuring a signal with a parametric amplifier. But physically what happens is, imagine if you have a qubit and you prepare it in a superposition of 0 and 1 and measure, no measurement actually happens over an instantaneous timescale, and so there's going to be a diffusive process where the atom collapses either to 1 or 0 over a finite timescale. And so that timescale gives us a timescale over which we can do feedback, just like in the previous slides. That feedback can come in as a feedback Hamiltonian. And some controller can take the measurement outcomes, which are continuous, and then apply some feedback Hamiltonian or superposition of feedback Hamiltonians conditional on that measurement record. So, in general, this parameterizes any kind of unitary operation on the system. So it's completely general. And the simplest way you might try to optimize this is just take your figure of merit, maybe its fidelity or expectation value as a function of time. And after every infinitesimal amount of measurement that you apply, apply some optimized feedback rotation and try to maximize your figure of merit at every time step. And all this is pretty simple to state. It actually turns out to be fairly difficult to solve in the general case. But it turns out there's some nice tricks. So one trick is simply to assume that you're doing a locally optimal feedback protocol, and so you've always applied the optimal rotation in the previous time step. And so that means that if you plot your figure of merit, for example, fidelity, as a function of rotation angle, and I'm only plotting one theta here, so in the previous slide we can imagine having multiple thetas and parameterizing any unitary. But in any case, at any given time step, your figure of merit is going to be optimized at theta equals 0. And so if you apply an infinitesimal amount of measurement, or you acquire a little bit of information from your quantum system, then the optimal rotation angle should be pretty close to 0 at this point, which means that you can expand it as a function of dt and dw, where dw parameterizes the sort of the random quantity coming from your measurement outcome. And the other thing I want to show on this slide is that if you use this kind of series expansion, you can actually derive a general form, a closed form expression for the locally optimal feedback protocol for any kind of quantum measurement. So essentially take any quantum system in which you can measure with high enough collection efficiency that this kind of feedback, or this kind of master equation description of the measurement process is valid. You can immediately use these equations to derive a feedback protocol that will let you maximize the expectation value of some operator or prepare any quantum state that's possible to prepare with your large feedback controls. And although I've only written this here for a single control variable theta, this thing actually generalizes for any possible or allowable feedback Hamiltonians that you want. And so you can actually take this formalism as a black box and it can spit out exactly what your optimal Hamiltonian is. This is my last slide, just to outline sort of applications that show maybe a bit of the power of this formalism. This is a list of some of the sort of standard quantum feedback protocols in the literature. One of them is this rapid purification method of Kurt-Jacobs that shows that you can purify a qubit faster using quantum feedback. Another one is this adaptive measurement protocol that shows how to create a canonical phase measurement. In all of these cases, the equation that I showed you on the previous slide can reproduce the result known in the literature, and even in some cases generate new results. So at this point, I've linked the relevant papers in the description, so thank you very much for joining, and if you have any questions, feel free to contact me. And thanks a lot for joining.